what we are going to do is have the regular presentation, and then after each presentation, so I'll ask the audience if there are some questions. We'll look also into the chat, and then continue. So in principle, there will be 5 to 10 minutes for questions. Okay, so Ningning, perhaps do you have the slides ready?
Yes.
So let's let's at least share them, okay? So because the session will start in 2 minutes.
Can you see the slides?
Yes.
Okay.
Okay, let's then start.
Okay. Hello, everyone. My name is Hou Ningning. I'm a PhD student at the Hong Kong Polytechnic University. The paper I will present today is titled CloakLoRa, a covert channel over LoRa PHY. This is the joint work with my supervisor, Dr. Zheng Yuanqing. As we all know, long-range technology, which simplified as LoRa, is one of the most promising LP1 technologies. LoRa works with narrow bands and can transmit up to 10 kilometers with a battery life of up to 10 years. Thus, LoRa is very suitable for resource-constrained, long-range, and low data rate applications. For example, against COVID-19, one Italian company equipped a medical gas value monitoring system with LoRaWAN for data transmission, which allows hospital staff to remotely monitor and control the amount of oxygen remaining in the cylinder. Besides healthcare, LoRa has also been used in smart city, smart home, smart supply chain, and so on. However, the security issue of LoRaWAN is a big concern. For IoT applications, security is more important than ever. Then we ask a question: is LoRaWAN secure? This figure shows the LoRaWAN topology. The sensor data will be encrypted at the network layer and the application layer. These two layers use AES encryption to secure the end-to-end communication. However, the above message encryptions only work at the upper layers, while the LoRa physical layer remains less protected, which leaves LoRaWAN vulnerable to attack. LoRa physical layer uses chirp spread spectrum to modulate data. How it works? It uses this initial frequency of the chirp to indicate data. Assume we need to modulate 2 bits with each symbol. Then we need 4 different chirps with different initial frequencies. For example, 01 uses F3 as the initial frequency. For demodulation, LoRa also examines the initial frequency of chirps. However, there are other physical layer parameters, for example, amplitude, phase, and waveform. These parameters are overlooked by the receiver, which leaves opportunities for attacker. Our work aims to use amplitude to build a covert channel over LoRa PHY. To achieve this goal, we first summarize the design requirements of covert channel. First, the channel should be covert to regular LoRa transceiver. Covert means secret. The legitimate LoRa transceiver should not be aware of the existence of the covert communication. Second, the channel should be efficient to support more information leakage. And third, the covert channel should not substantially affect the regular LoRa communication. Then I introduce the high-level idea of our covert channel. In our scenario, victim Alice is compromised to leak covert information. Alice can be a LoRa node or LoRa gateway. As for attacker, an attacker can be an insider who aims to secretly send out sensitive information. An attacker can also be a LoRa node manufacturer who can modify the firmware of sensor node or add micro hardware components in the PCB board before delivering the bugged sensor to users. Then the signal transmitted by Alice contains both original CSS information and AM covert information. The legitimate receiver Bob receives CSS LoRa packet. Since Bob only examines the initial frequency but overlooks amplitude, Bob cannot be aware of the existence of covert channel. While the covert receiver Carol receives AM covert information, we assume that only Carol knows the implementation details of covert channel. Therefore, Carol can leverage the knowledge of implementation to detect the existence of a covert channel and secretly receive the covert data. Carol only extracts the embedded covert information and does not need to decode a regular LoRa packet. Thus, we can build an AM-based covert channel over LoRa PHY. And this channel is covert to regular LoRa transceiver. And so our design can meet the first requirement. And now we move on to the second requirement, to improve the efficiency of covert channel. To build a covert channel using amplitude modulation, a strawman approach is to vary the transmission power of a LoRa node before every packet transmission. Commodity LoRa devices allow users to configure the RF output before sending a packet. We can use lower power to indicate bit 0 and higher power to indicate bit 1. A covert channel receiver may measure the RSSI to infer the covert information. However, this packet-level amplitude modulation approach cannot provide sufficient data rate for practical covert channel applications because the duty cycle of LoRa is only 1%. So how to achieve high data rate covert transmission under the constraint of low duty cycle? Using power of one packet is low efficient, but what if using one chirp? Each LoRa packet contains multiple chirps. Ideally, if we can vary the amplitude of chirps, we can transmit covert data at higher speed. So the advanced solution is to enable chirp-level amplitude modulation. We propose to add an AM component to generate amplitude-modulated LoRa chirps. The workflow of our advanced covert transmitter contains 2 chains. The lower chain is responsible for generating regular LoRa chirps, while the upper chain generates AM signals. We multiply these two signals before transmission. By configuring the duration of AM signals, we can modulate LoRa signals at chirp level. And we further test the feasibility of this idea by using software-defined radios. These two figures shows the results. The upper figure is the LoRa packet in frequency domain, and the lower one in time domain. We control the amplitude of payload chirps to high and low states alternatively. The amplitude in frequency domain is color-coded. Light color indicates higher power, while dark color indicates lower power. If Alice used chirp with lower power to indicate bit 0 and high power to indicate bit 1, a series of covert bits can be embedded, and Carol can use an envelope detector to decode the covert information. Now the question is how to apply this to commodity LoRa nodes. Commodity LoRa devices don't allow users to configure the power of chirps. Then how to change the amplitude of each chirp? And we use simple passive components to address this problem. The figure shows our prototype with CloakLoRa. The red one is LoRa Shield and the green one is Arduino Uno. The LoRa Shield is set on Arduino. We add a branch circuit to modulate LoRa signal at chirp level, and this branch circuit only contains a transistor and a resistor. So what's the magic of these simple passive components? As shown in this figure, the switch in the new branch controls the electric current flows through the antenna load. When the state of the switch is off, the current, denoted as I, flows through the antenna as if there's no external circuit. When the state of the switch is on, as a portion of current is leaked through the added circuit, denoted as I prime, the current flows through the antenna becomes I minus I prime. As such, the RF power of the outgoing signal becomes lower when the switch is on, and become higher when the switch is off. As a result, by altering the state of the switch, we can generate changing amplitudes. We can also control the lower amplitude value by adjusting the two. In practice, these passive components can be integrated in a tiny SPI chip or PCB board of LoRa nodes before delivering them to the customer. This shows LoRa PHY is vulnerable to attack. As for covert receiver, we use receive-only SDR dongle because it only needs to extract amplitude changes. The upper chain of this figure shows the workflow. Basically, we use envelope detection to extract the amplitude changes. Until now, we have built AM-based covert channel with high data rate. Now we focus on the third requirement. Since we vary the amplitude of LoRa signal, the regular LoRa communication may be impacted. In our work, we use modulation depth, D, to represent the signal variations of carrier waves. We define D equals to M divided by A, where M is the peak-to-peak changes and A is the original carrier amplitude. For LoRa covert channel, a larger D is preferred as it indicates a higher SNR at the covert channel receiver. However, for Bob, the legitimate LoRa receiver, a larger D means weaker signal strength of part of the regular LoRa chirps. These two are conflict. So in practice, Alice can actively adjust the D and transmission power to make sure the covert information can be received by Carol, while regular LoRa packets can be correctly decoded by Bob. In our prototype, we use a fixed D for proof of concept. For evaluation, we use both CloakLoRa node and software-defined radios as covert transmitter. and we use low-cost receive-only SDR dongle as covert receiver. We conduct experiments with these devices in our campus in both outdoor and indoor environments. And we use bit error rate, throughput, and symbol error rate as evaluation metrics. The tables show the default parameter settings of covert channel as well as regular LoRa communication. We configure the regular LoRa works at 915 MHz ISM band and set the bandwidth to 250 kHz. For the covert message, we set payload length to 30 bits and default modulation depth to 0.1. We first explore the effective communication range. We use USRP as covert transmitter, as the red dot shows, and we keep it stationary. We place the SDR dongle at 4 different positions in our campus, as the yellow dots show. The whole test bed spans about 70,000 meters square. Results show that receivers at ABC with line of sight path to transmitter can achieve less than 2% bit error rate, while receiver at D, though closest to the transmitter, without line of sight path, gets much larger bit error rate. Actually, there are multiple concrete walls and scaffold between them, making covert signal too weak to be decoded correctly by the SDR dongle. Next, we evaluate the throughput of covert channel. We configure the transmitter to transmit LoRa packets once per second, and the payload length of covert message is 30 bits. This figure shows the throughput of covert channel in different SNR scenarios. If we use power of the whole LoRa packet as covert information, we can only transmit 1 bit per second. But if we use chirp level amplitude to encode covert information, we can transmit 30 bits per second. We can further improve covert channel throughput by extending payload length of covert packets. We then investigate the impact of covert channel on regular LoRa communication. This figure shows the symbol error rate of regular LoRa packets versus D under different SNR scenarios. We can observe that for regular LoRa packets, a larger D leads to higher symbol error rate. But in high SNR scenarios, even when D is 0.9, LoRa receiver can still decode the LoRa packets with SER less than 4%. D has bigger influence on LoRa communication when the SNR is low, while it slightly influences regular LoRa communication when the SNR is high. To conclude, we investigate the vulnerability of current LoRaWAN physical layer, where the legacy end-to-end security mechanisms fail to protect. We also implement a hardware prototype of covert channel with commodity LoRa node. We conduct comprehensive experiments with COTS LoRa node and software-defined radios. A covert channel is actually a double-edged sword. It can be used by attackers as well as defenders. In the future, we plan to use covert channel to do something good. For example, we can use covert channel to transmit coordinate information or even enhance LoRaWAN security. Thank you for your listening, and I welcome questions.
Thank you. Okay, so we have circa 30 minutes for questions. So you can ask your questions via the session question and answer, or simply speak. So are there any questions? Okay, so to break the ice, let me start by doing one. So Ningning, in the paper, so in the experiments that you have run, The experiments relied on a distance between transmitter and receiver of 250 meters. How will CloakLoRa work with longer distance?
Okay, thank you for your question. You mean that the covert transmitter and the covert receiver, the distance is larger than 250 meters?
Yes.
Yes. I can show one picture about this. This figure shows the amplitude of signal recorded by Carol, the covert receiver, at different distances. As shown in this figure, if the if the distance between Alice and Carol is larger than 250 meters, the amplitude variations received by Carol may be a little bit weak for Carol to receive all the covert information. But Carol can still observe some amplitude changes. So if Carol is further placed, it can only receive a portion of the covert information. So if Carol moves further away from Alice, for example, in this figure, the distance is larger than R2, maybe the Carol cannot reliably receive even 1-bit information because it cannot observe any amplitude changes. So the distance for distance of the reliably covert data decoding has limitation.
Okay. And do you think that the 250 meters, or here you show up until 400 meters, is enough for LoRa scenarios?
I think yes, because the attacker or the covert receiver is relatively flexible in our scenario or in practice. The attacker can put their receiver close to the transmitter. Since this amplitude-based covert channel is orthogonal to the CSS demodulation, and the current LoRaWAN cannot observe this. So I think it doesn't matter for the covert receiver to be a little bit nearer to the transmitter.
Okay, thank you. Are there any other questions? Okay, so we still have time. Thank you, Ningning. Nonetheless, if there are no more questions, I would start by presenting the second paper and ask Weifeng, to get ready. So the second paper on this session is AdapLoRa, resource adaptation for maximizing network lifetime in LoRaNet. So this is presented by Weifeng Zhao, who is a PhD candidate at the University of Electronic Science and Technology in China. And his research interests include low-power wireless networks and edge computing.
And is the slides available now?
Yes.
Mm-hmm. Okay, wait a second. Good afternoon, everyone. This is Weifeng from the University of Electronic Science and Technology of China. I am very excited to be here today to share our research on LoRa networks, especially about the resource adaptation to improve the network lifetime. Well, should I make my picture on the upper right? Let me see.
Yes, if possible, would be nicer.
Is this one? Okay, I can wait. What? Maybe like this. Okay. LoRa is a technology of LPWANs which has attracted much attention on the Internet of Things applications, such as the smart city, etc. It can achieve dense and large network deployment with low power consumption on the end devices. There are several technologies of LPWANs such like LoRa, Sigfox, and NB-IoT. Among them, LoRa is one of the most promising ones because of its open standard and low complexity for deployment. Okay, now let us see what does LoRa signals look like. The signals are called chirps, whose frequencies increases or decrease linearly, just like this figure shows. And if we turn the signal to the frequency domain, we can see the linear increasing more clearly. And there is an important parameter in LoRa or C8 resource called spreading factor. The spreading factor can control the transmission reliability, thus the communication distance of LoRa signals. And it also affects the time on air of a signal. For example, the transmissions with larger spreading factors has longer time on air, like this figure shows. So they will consume more energy for transmission, but they have much more reliability and so fewer retransmissions. And to see this impact more clearly, we have this example. Assuming we have one gateway to receive packets from two end devices here, which uses different spreading factors to reach the gateway. And transmitting the same packet from them will spend 14.6 milliseconds for spreading factor 7 and 320 milliseconds for spreading factor 12. So there is a 22 times longer transmission time for spreading factor 12. As a result, the right end device will run out of its battery much faster than the left one. And this energy unfairness will reduce the network lifetime because basically the network is considered to be broken when the first end device is dead. For the fairness in LoRa networks, the literatures have focused on the allocation of resources, such as the channels, the spreading factors, and transmission power to balance different end devices, the performance, which is usually formed as an optimization problem. As a result, different devices will send packets with different resource allocation, like channels or spreading factors. And for example, some work use the min-max fairness optimization to achieve the fairness of collision probability. Here, the P collision is the probability of collisions between the end devices. Or some works will, use optimization problem to balance the energy efficiency between the end devices. However, this static allocation is not suitable for real deployed networks because of the dynamics of wireless networks, wireless links. For the experiments, you can see the varying link conditions among them. This indicates that the static allocation is not efficient for improving the network lifetime, and an adaptive allocation scheme is needed. With this inefficiency, we propose AdapLoRa, an adaptive resource allocation in LoRa networks, which we call it resource adaptation. Before introducing AdapLoRa, we're going to answer two questions here. The first one is, when do we adapt the resource allocation? And the second one is, how do we adapt the resource allocation? And yes. Optimally, we would like to run the optimization problem every time the channel condition is changing. Like in this figure, the channel condition varies among the time. But this is extremely difficult, and there is a unique feature in LoRa networks. The overhead of downlinks has great impact on the resource allocation. The downlinks are transmissions from the gateway to the end devices. Basically, the overhead of downlinks consists of two parts: the transmission latency and the energy consumption. For the latency, usually a LoRa network can cover a lot of end devices, for example, hundreds of them. But the problem is LoRa gateways send downlinks to the end devices in a unicasting manner, which means this gateway has to notify the end devices to use new resource allocation one by one. And this will cause large latency to notify all the end devices. For example, if we have 1,000 end devices, it may take almost 1,000 seconds to complete the downlinks, which is not acceptable for link dynamics. As for the energy consumption, assume we have 4 end devices here, and they first send their own data to the gateway. After that, they will wait for downlinks from the gateway. The gateway will calculate a new allocation and send a new resource allocation to different devices. Note that some end devices do not need to change their allocation, so they do not need to receive any packet. In this case, only these 2 devices have to receive the new allocation packets. As we know that the battery power on a low power device is mainly consumed by the active MCU, and receiving a packet will also consume a lot of energy. Basically, it's almost half of that of transmission in LoRa devices. So these 2 devices will consume additional energy for packet reception, and their lifetime will be reduced. This energy consumption can lead to further energy unfairness and lower or shorter network lifetime. To solve these problems, our proposed method works as follows. The gateways will periodically evaluate the network lifetime improvement with different resource allocations. Specifically, the end devices in a LoRa network will send their packets to the gateway with an initial allocation 0. After receiving the packets, the gateway will estimate the network lifetime with this current allocation 0. And then it will compare this network lifetime with different resource allocations to see if the network lifetime can be improved by a new allocation. If it does, the gateway will send the new allocation 1 to the end devices. And the end devices will receive this allocation and use this allocation to send their packets in a new iteration and go to the next one. Okay, let's start from the first step here. The gateway can obtain the bit error rate of the packets from the end devices and calculate the network lifetime at T1, which is used as a baseline of the resource allocation. And now we go to the second step. At this step, the gateway will obtain the network lifetime with different allocation with our proposed network model and make a comparison. If a new allocation can lead to longer network lifetime, the gateway will send downlinks to these end devices to notify them that they need to change their resource allocation. And the 2 overhead we mentioned before is also solved in this step. To reduce the downlink latency, in this step. To reduce downlink latency, here, we solve the optimization problem and try to improve the network lifetime using the shortest downlink latency. For example, if we have 4 end devices, using different spanning factors from 7 to 12, they will have different time on air of downlink packets. So we first try to change the allocation of the left end device with spanning factor 7. If we cannot find a new allocation to improve the network lifetime, we will go to the next one and we will try to change the device with spanning factor 9. until we can find a satisfying resource allocation to achieve an acceptable network lifetime improvement. To evaluate different resource allocation for the network lifetime, we use the bit level network model to get the network lifetime. Specifically, the network lifetime can be modeled by how many cycles can an end device run. In this equation, EI means the total power of an end device battery. ET, ER, and ES are the energy consumption for transmission, reception, and sleeping. And RI is the packet reception ratio, so it is related to the transmission reliability. To calculate the packet reception ratio here, we rely on the symbol error rate. This probability is that the power of the expected symbol is less than the interfering symbol plus the power of noise. And this is related to the transmission power, related to the spreading factor and the channels. So with this proposed model, we can estimate the network lifetime with different resource allocation, and we can find an improvement for with the shortest downlink latency. So we can solve the above challenges that we mentioned before, like the latency overhead and the energy consumption overhead. We evaluate the AdapLoRa by deploying real testbed on our campus. We have deployed 4 gateways on the roof of 4 buildings. We compare AdapLoRa with EFLoRa, which is a static allocation. And the end devices will use the original resource allocation without changing amount time. Let's see the network lifetime comparison first. We can see that AdapLoRa can improve the network lifetime of EFLoRa with different number of gateways. Also, we use the residual energy consumption, residual energy in the network to represent the energy fairness in the LoRa network. And AdapLoRa also achieved better energy fairness in this network. And then we decompose AdapLoRa to show the performance gain of different parts in this scheme. We first implement a simplified AdapLoRa which does not consider the overhead of downlinks. And we can see that this simplified AdapLoRa doesn't consider the overhead. And this consideration can contribute the network lifetime improvement for about 31%. And we also evaluate the impact of transmission power allocation. We can see in this figure, without the transmission power allocation, the network lifetime will be reduced for about 28%. And to conclude, this work is the first one to solve the resource adaptation problem considering the downlinks overhead. And we estimate the network lifetime with periodically updated network model. And then we propose a fine-grained network model considering the impact of bit level error correction scheme. And so we embed the FEC, new FEC scheme in this bit level model. And thank you for listening. This is my presentation. It's done now.
Okay, thank you. Are there any questions? Okay, so I have a question, then perhaps again this breaks the ice to the audience. So Weifeng, AdapLoRa has been evaluated on static scenarios, so where the end nodes are not mobile. So you present an improvement in terms of network lifetime, so you prolong the network lifetime in circa 23%. Do you think this would hold if the end nodes would be mobile?
Sorry, I'm not getting you very clearly. Could you repeat your last sentence?
Yes, so I'm going to write it also so that
just the last one, yeah.
It's on the session. But the question is, if the end devices were mobile, do you think you would have the same improvement? Did you consider this?
Yeah, that's actually this is a very practical question, because we didn't consider the mobility of the devices. We consider the multiple gateway scenarios, and the devices, if the device is moving across different gateways, the transmission reliability will be quite different, because they can be received by multiple different gateways. So the performance of this AdapLoRa will definitely be affected. Yes, let's just see that.
But do you think you could apply the mechanism also to mobile environments?
Sorry?
Would you be able to apply AdapLoRa to mobile environments?
Yeah, achieving the mobility of, not achieving, maybe considering the mobility of devices will be a next move to further improve the LoRa networks, because the mobility is actually very common in many applications, IoT applications.
Okay, thank you. So any other questions?
Hello, I have a question.
Hi.
Yes, can you state your name, please?
My name is Ningning. I'm the speaker of the previous slides.
Yes.
My question is, does the resource allocation contains the channel condition at different frequencies? I mean, different central frequencies may have different channel condition. So sometimes when, for example, when the SNR is low, the downlink or uplink packet may be not correctly received by the end device or gateway.
Yes, yeah, the channel is considered in the network model, because it is highly related to the transmission reliability. It will have different interference among the end devices. If many devices are using the same channel, their bit error rate or the packet error rate will increase very fast.
Oh, okay. Oh, thank you.
Okay, are there additional questions?
Can I ask one question? Can you hear me?
Yeah, I can.
In your presentation, I think you mentioned one of the related work published in the NSDI 2020.
Yes.
And that paper, I think that is quite related to your work. So why don't you compare your performance with that work?
This one?
Yeah.
This paper mainly consider the multipath effect for LoRa signals, and since we're considering the resource allocation in LoRa networks, so we only consider the selection of the spreading factors or the channels, and we did not consider this multipath effect to empower the signals itself. And we use this figure to show the dynamics of the wireless links. Yeah.
Okay, so in the resource allocation, do you select a different frequency, different frequencies, or just focus on one frequency?
We consider different frequencies as different channels. Like in basically like in the US, the channels we have use 8 channels for the gateways.
Okay. Okay. Thank you.
Thank you.
Okay, we still have some minutes. Any additional questions? Okay, so thank you. Let's then proceed to the third paper. So the third paper is SCLoRa. So the paper will be presented by Bin Wu from the University of China. He is a master candidate at the School of Computer Science. His research interests concern cyber-physical systems.
Okay, can you see my screen?
Yes.
Okay. Hello, everyone. My name is Hu Bin. I'm a master candidate at Southeast University. I'm honored to have the opportunity to present at the conference. The paper I will be presenting today is titled SCLoRa, Leveraging Multi-Dimensionality in Decoding LoRa transmissions. Over the past few years, IoT has become one of the most important technologies of the 21st century. By connecting every physical object in the world, IoT has changed a lot of aspects in our life. Due to the needs of new applications and series, the low-power wide area network technologies, including LoRa, MBLT, and Sigfox, have been emerging as popular technologies in recent years. LPWAN equipment generally has the characteristics of long transmission range, low power, low cost, and low data rates. As one of the representative technology of LPWAN, LoRa can reach a communication range of 10 kilometers. Besides, low power requirements in LoRa allows for the creation of battery-operated device that can last for up to 10 years. The data rate of typical LoRa is between 0.3 to 5.5 kbps, and the RSSI minimus is about minus 120 dBm. And many LoRa-based applications are developed, most recently. Dealing with increased COVID patient flow, Barcelona hospitals implemented a North Code solution using LoRa awareness sensors with geolocated buttons from MBWay. According to IoT Analytics LP1 Market Report 2018 to 2023, global LP1 connection is expected to reach greater than 1.1 billion devices by 2023, with LoRaWAN emerging as the de facto unlicensed LP1 standard. And there are about 143 LoRaWAN network operators distributed in 161 countries. Due to the deployment of so many devices and the long communication range of LP1, a large number of end devices may coexist at the same area. As shown in the figure, the end devices are deployed at these different locations, and a situation may occur where multi-end devices transmit data simultaneously to the base station. Therefore, the concurrent transmissions may lead to serious modulation errors and even packet loss, and the throughput of the network will decrease accordingly. To address the problem of LoRa concurrent transmissions, existing approaches are divided into two categories: the max solutions and the fixed solutions. Max solutions address collision issues through collision detection and transmission scheduling. And the physical solution address collision issues mainly based on the unique feature of LoRa. Although this multi-layer approach improves the throughput and the reliability of the network, The limited power budget and the low cost of LoRa nodes make it challenging to deploy sophisticated MAC methods. Existing physical solutions eliminate physical layer features such as hardware frequency offsets and frequency changes that are unique across different LoRa nodes. Admittedly, these techniques have the capability to decouple and demodulate collided concurrent transmissions. They are limited in solving collisions in large-scale LoRa networks, since they rely on single LoRa feature, which is not fine guaranteed enough for signal separation of bursty LoRa transmissions. To support bursty LoRa in the explosive IoT area, we try to utilize multiple LoRa features at the same time to separate concurrent uplink transmissions. We summarize the 4 dimensions in LoRa transmissions: channel, spreading factor, frequency, and power. The idea of leveraging multi-dimensionality in decoding collided LoRa transmissions is similar to the classification as shown in the figures. When there is only one dimension of information, it is not easy to distinguish these dots. However, the multi-dimensional information can help to improve the resolution of collided signals. So, how to combine multi-dimensional features to separate collided packets? Next, I will introduce how SCLoRa implements the combination of multiple features, and SCLoRa are divided into 2 parts. Core design is a design for symbol classification, which mainly contains spectral coefficient, cumulative spectral coefficient, and peaks evaluation. And enhanced design contains spectrum leakage elimination and preamble detection. Through the design of SCLoRa, the collided transmissions can become separated transmissions. Next, I will focus on the core design. So let's start by looking at the spectral coefficient. The spectral coefficient is also called the Fourier series coefficient, which is a measure of the magnitude of each harmonic component in the signal. Through FFT, we normalize the spectral coefficient as shown in this equation. From the equation, we found that the spectral coefficient of the symbol is associated with the power of the signal and the frequency offset. Through the spectral coefficient, the information of the 2 dimensions in LoRa are combined effectively. According to the analysis, we draw the conclusion that the spectral coefficients are generally stable within LoRa transmissions and are different across distinct LoRa transmitters. As shown in the figures, 2 different symbols in a packet have the same spectral coefficient at their frequency because the amplitude of their signals and the time offsets of each symbol from the window are constant. So far, we have combined the information of the 2 dimensions of LoRa by utilizing the spectral coefficient. Then, can the spectral coefficient be directly used to separate collided transmissions in practice? The answer is no. Since LoRa transmissions are generally affected by the dynamic channel feeding, the spectral coefficient is volatile in practice. The figure on the left depicts the error between the theoretical spectral coefficients and the spectral coefficient calculated from the received signal. The figure on the right demonstrates the statistics of the spectral coefficients for different LoRa transmitters. Similar to the theory, the spectral coefficients are generally stable within a LoRa transmission and are different across distinct LoRa transmitters. This motivates us to utilize the spectral coefficient in a more sophisticated way. To solve the problem, we define cumulative spectral coefficient as this equation, which counts the cumulative changes of spectral coefficients over time. As shown in the figure, the target symbol cannot be simply extracted as a result of the same spectral coefficients of 3 peaks. When the window slides to the left or right, the sampling points of the two interfering symbols increase accordingly, while the sampling points of the target symbol decrease. In theory, the sampling points of the target symbol should decrease when the window slides to the left or to the right, and the spectral coefficient should decrease accordingly. So we can determine the target symbol based on the changes of the spectral coefficient. By exploiting this phenomenon, SCLoRa manages to increase the difference of cumulative spectral coefficient between the interface symbol and the target symbol for identifying the target symbol.
Hello. So the presentation seems to be frozen.
Yeah, I cannot hear the presenter either.
Right. So who been?
Yes.
Possibly, are you in still?
Perhaps put the recorded video there, maybe.
Maybe he can come back in a minute. Let's wait for 20 seconds.
Yes, we have time. Let's just see, because I can see him online, but not sure. Hello.
Yeah,
Binhu?
I'm trying to
get him back.
ask him to play the video and
Okay.
ask him, but he doesn't seem to reply. So it must be something with his connection.
Yes.
Maybe on behalf of him, maybe the Zoom master, can you play the video on behalf of him?
Sure. So, Sophia, are you okay with playing the
Yes,
video?
of course. Yeah.
Fine, I'll do that.
Hello, everyone.
Okay.
My name is Hu Bin.
Hello, Noelia. Can you
Master
please
candidate at
push it?
Southeast University. I'm honored and proud to have the opportunity to present at the conference. The paper I will be presenting today is titled SCLoRa, Leveraging Multi-Dimensionality in Decoding Collided LoRa Transmissions. Over the past few years, IoT has become one of the most important technologies of the 21st century. By connecting every physical object in the world, IoT has changed a lot of aspects in our life. Due to the needs of new applications and series, the low-power wide area networks technologies, including LoRa, MDRT, Sigfox, and Witness, have been emerged as popular technologies in recent years.
Can you please push the video?
LP1 equipment generally has the characteristics of long transmit range, low power, low cost, and low data rate. And many LP1 based applications, such as selling monitoring system, SC and well-being monitoring, agricultural monitoring, are developed.
We have listened for this.
As one of the presentive technologies of LP1.
I'm sorry, but I don't have a chat. So Noelia, can you hear us?
Communication range of 10 kilometers.
Hey, hello.
Chat, okay.
Hey, hello.
Allows for the creation of battery-operated device that can last for up to 10 years. The data rate of tactical LoRa is between 0.3 to 5.5 kbps, and the RSSI minimum is about minus 120 dBm. In the COVID-19 context, governmental authorities and commercial companies have been looking at recent technologies such as IoT to find all sorts of solutions to respond to the crisis. Social distancing, people tracking, and asset monitoring have become crucial aspects of keeping the situation under control. Most recently, dealing with increased COVID patients flow, Barcelona hospitals implemented a nurse call solution using wireless sensor with geolocated buttons from MBWay. According to IoT Analytics LP1 Market Report 2018 to 2023, global LP1 connection is expected to reach greater than 1.1 billion devices by 2023, with LoRaWAN emerging as the de facto unlicensed app.
Sorry, Sophia, did you want to do something in the video?
Yes, so Hubin had already presented this part, okay? So we need to push the video up to the point where
I cannot hear you.
Can you hear me?
So there is no option to push the video?
Hello, can you hear me? Can you forward the video?
Sorry, can you repeat?
Can you forward? So the video, you need to push it.
Yeah,
a little
okay.
bit.
Up to which
Let me see.
minute?
Can be there. Can be there. Yes.
There?
This
Okay.
point is fine.
Okay, thank you. Perfect.
The spectral coefficient is for light in practice. Figure on the left depicts the error between the theoretical spectral coefficient and the spectral coefficient calculated from the received signal. The figure on the right demonstrated the statistics of the spectral coefficients for different LoRa transmitters. Similar to the theory, the spectral coefficient are generally stable within LoRa transmission and are different across distinct LoRa transmitters. This motivates us to utilize the spectral coefficient in a more sophisticated way. To solve the problem, we count the cumulative changes of spectral coefficients over time. And the cumulative spectral coefficient is shown as this equation. From the figures, we found that the target symbol cannot be simply extracted as a result of the same spectral coefficients of 3 peaks. When the window lies to the left or right, the symbolic points of the 2 interfering symbols increase accordingly, while the symbolic points of the target symbol decrease. By exploiting this phenomenon, SCLoRa manages to increase the difference of cumulative spectral coefficient between the interfering symbol and the target symbol for identifying the target symbol. The figures depict the result of cumulative spectral coefficients of the target symbol and the interface. The figure on the right reflects the difference of the cumulative spectral coefficient of the symbols when the signal boundaries of the 2 symbols are adjacent. When the boundaries of the signals are close, the power can be used to distinguish the symbols. By calculating cumulative spectral coefficients, we not only reduce the influence of signal amplitude fluctuation, but also increase the degree of discrimination between the peaks in the window with similar spectral coefficients. The next step is to evaluate each peak based on cumulative spectral coefficient as shown in the equation. Through the above process, we can demodulate and classify the received symbols, so we can get separated transmissions from the collided transmissions. Next, I will introduce the enhanced design of the SCLoRa. Due to the limited sliding window, the FFT results of LoRa signal suffer from spectral leakage as shown in the figure on the left. This interface comes from the spectral line instead of the real collision symbol. To elevate this issue, we utilize different window functions to flag the original signal. To detect ongoing LoRa transmissions, SCLoRa utilizes the preamble detection, which are based on the continuously repeated peaks with the same frequency and spectral coefficient in the spectrum. As shown in the figure, the preamble can be detected according to the red peaks. To evaluate the performance of SCLoRa, we design a LoRa nodes which use the STM32 chip as the main control chip, SX1278 as a radio frequency chip, and the lithium battery to power the entire equipment. And the USRP serves as the base station. We mainly perform experimental evaluations on the campus and the laboratory. In the experiments, we mainly compare SCLoRa with the 2 technologies, the baseline, LoRa, and the state-of-art, F-track. To explore the impact of the number of nodes in the network on the performance, we conduct the following experiments. The figures show the result when the SF is 8, 10, and 12 respectively. The result shows that the F-track doesn't perform well when the SF is small. And the SCLoRa achieve about 2,100 bits each second when the number of nodes is 12 at SF8. In general, the throughput of SCLoRa is 2.7 times of F-track. To explore the performance of SCLoRa at different distances, we fix the base station and place 4 LoRa nodes at different locations on the campus to test the throughput. As a result of the hardware limitation and the parameter settings, the communication distance of our equipment would reach nearly 1 kilometer. From the result, we found that as the communication distance increase, the throughput decrease, and the throughput of SCLoRa is about 1.7 times of F-track. We evaluated the performance of SCLoRa under burst traffic. The burst traffic may be caused by two reasons: dense deployment and the expanding packet delivery rate in the network. And we increased the duty cycle of the device to simulate burst traffic series. The evaluation results show that SCLoRa performs best, which achieve a 7.1 times throughput of F-track. And we achieve different degrees of collision to explore collision resolution capability. To make all nodes collide during transmission, we set the duty cycle to be greater than 50% in the experiment due to the high duty cycle of the transmitted signal. The boundaries of collided signal are close, especially when the number of colliding nodes increase. Since SCLoRa considers the information of frequency offset and power in 2 dimensions, it is easier to distinguish the symbols in the case of such symbol mixing. In general, SCLoRa achieved a 6.7 times symbol reception rate of F-track. In this paper, we propose a novel physical solution called SCLoRa to solve the collision of concurrent LoRa transmissions. SCLoRa is the first to examine multiple Unicode features for distinguishing concurrent LoRa packets. This enables SCLoRa to work well in dense networks with bursty traffic. To be resilient to the dynamic environment, SCLoRa introduced cumulative spectral coefficients, which are determined by the Unicode amplitude and the frequency offset. We evaluate SCLoRa with USRP and the community LoRa radios. Experiments across different settings demonstrate the effectiveness of SCLoRa, achieving a 3 times network throughput of the state of art. I'm glad to have the opportunity to present our work at such a top-level international conference. I'd like to thank you for your patience and concern in listening to my presentation. If you have any questions, please feel free to connect me.
Okay, so it would be great to see if Hubin would be in the session, but I cannot find him. I've just sent him a mail. So Hubin, are you in the session? I cannot see you in the list of participants, so just confirming. Interesting. Okay, he's actually he contacted me via WOVA, so possibly he cannot connect. So I'm afraid that we cannot ask him questions. Okay,
we can still ask through LoRa. LoRa is possible to ask questions.
Yeah, it is, but I'm afraid that he's not really responding. Okay, so we responded a couple of minutes ago. Of course, yes. So if you have additional questions, you can ask the authors online via the session questions and answer or directly. So this is the last paper. So this concludes the session. Thank you all, and see you in the next session.
Thanks, bye.
Bye.